everybody. This video is going to be what I call a crash course on gases and their behaviors. One of the things that's tough about this chapter for me as a high school teacher is that a lot of the middle schools cover gases and how they behave and what their properties are, which is great. It's very engaging to students. It's something young students can often understand. The problem is that not every middle school teacher maybe covered it. They may not have covered it in the same depth. So everybody's coming in at a very different place when it comes to this topic. So rather than making this an official set of lecture notes, what I'm doing is I'm making this available. I'm encouraging you to watch it. It's a great refresher if you already learned it. If you didn't learn it, you can learn it through the video. You can come ask me questions. You can read sections out of a book, right? We can find more videos if you like. But because we have such a variety of background knowledge on this topic, we're not going to make it an official set of notes. So please, please, please come see me if you need help, okay? All right, so first, what exactly causes pressure? We experience pressure in our lives all the time, and I don't just mean from school and parents and friends and all of that, but right, like the pressure in your tires or maybe in some kind of an oxygen tank. There's pressure that keeps the carbonation inside the soda, inside the can before you open it. Balloons inflate because of pressure. Some of you might have parents that have a pressure cooker. This one is an old-fashioned pressure cooker. These days I should probably update it and put a picture of an Instapot, right? Because that's like the modern digital version. But these are all examples of pressure that we can see all around us. It describes and explains how a lot of common everyday things work. So the gas particles zoom around really, really fast. They move in random motions. They don't have a brain, right? They're not deciding, oh, I feel like going to the left. They go until they hit the side of a container and then they bounce off. And when we say they go fast, I mean really fast. Like helium goes 3,000 miles an hour. Air is a mixture of a lot of things. It's primarily oxygen and nitrogen, which is a little bit heavier. So on average, it goes about 1,000 miles an hour. That means there's so many collisions per second. You are being hit over and over and over and over bazillions of times by air molecules. You know, if you got hit by a car going 1,000 miles an hour, obviously that would not be good, right? But an air, an oxygen molecule or a nitrogen molecule or a helium atom, they're so small that even though they're hitting you very, very hard, there's not much force behind them. But if you start getting more and more and more collisions, you can start getting more and more pressure. And so there can be a large cumulative effect. So it may not feel like we're being pushed and hit on by these particles because we're so used to it, right? We've adapted to that. But we are actually being hit by them quite often. So when the particles zoom around, they hit the edges of the container and they push on it. And that push is what the pressure is. Okay, it's a force being applied to a certain area. And so when we're doing these problems with containers and enclosed environments and stuff, the particles push on the container. And that's what's causing the pressure that we see and that we feel. We often diagram it like this with little arrows. The arrows are pushing onto it, right? They show you the direction they're going. You could even use the size of the arrow to show how fast they're going, right? So diagramming it like that's very helpful sometimes. We experience pressure from our atmosphere. If we're at sea level and at 0 degrees Celsius, the air molecules push on us with 1.03 kilograms for every centimeter squared. So every centimeter squared on you, you're getting pushed on with about 1 kilogram of force. And so it's kind of a clunky unit, kilograms per centimeter squared. We have a nice clean unit that we call atmosphere. So 1 atmosphere is that amount of pressure at sea level and 0 Celsius. If you change your temperature, that pressure you would experience would change. If you changed how high up you were, your elevation, that would change the pressure you experience as well. A very classic example of this is somebody at the bottom of a mountain and somebody at the top, like Mount Everest is a classic example. When you're at the bottom, you have more air molecules pushing on you, so you're going to have more collisions, you feel more pressure. When you're at the top, you don't have as much pressure up there. You're not getting pushed on as much. So we can have a lot of practice problems this chapter where we're asking to describe what would happen to the water bottle if he carried it up the mountain, or what would happen if you took a bag of chips up into the airplane, right? Those kinds of problems. We talk a lot about the pressure that things would experience due to the collisions. There's lots and lots of units of pressure. I wouldn't try to copy all of this down. You probably have, a glue-in for your notebook that has a lot of these, or you can, look them up on a reference sheet or something. But it's just nice to be able to convert to different units. Atmospheres is kind of our classic. One of the ways we can measure pressure is by something called a barometer. So originally the barometers used mercury. Mercury is not very safe, so they've actually replaced the barometers with a alcohol solution that's been colored. Usually it's put with red, food coloring so that it ends up a red color. But originally they were mercury. And what you do is you have a tube that has some mercury in it. It's a vacuum at the top. You turn it upside down into a, bowl or some kind of a container. And as the atmospheric pressure pushes down on the surface of the mercury, some of it will get pushed up this tube. And the unit that they use, millimeters of mercury, mmHg, comes from the fact that they would literally measure the height of this column. And if you're at 1 atmosphere, right, if you're at sea level and 0 degrees Celsius, this column of mercury would be 760 millimeters tall. And so we can literally measure this to be our unit of pressure. If you have high pressure in the atmosphere, it pushes really hard and it pushes really high up. The column will be much taller. If you have lower pressure, it won't push as hard, so you won't get mercury pushed as high up. So you'll get a smaller column, a shorter height, a smaller pressure unit. This is very similar to the barometer that we used when I was in college. We would have to run upstairs and have somebody check the barometer and then run back downstairs and write it on the whiteboard before we did our lab. Typically for me, I just look it up online. I just punch in our zip code and I say good enough. One of the teachers has a barometer at the end of the hallway, so sometimes I'll call him and I'll say, hey, what's the pressure in your room? And I'll write that on the whiteboard. So it's just kind of an old-fashioned one. I think it's fun to get to see pictures of those. It makes me feel really old that we used to use one like this. I didn't feel like college was that long ago. But when I look at something like this, that does seem like pretty ancient technology. All right, moving on. Kinetic molecular theory is a fancy way of describing the kind of rules that we think gases follow, the way they behave. We usually call it KMT theory. Yes, I know there's an extra T in that. Everybody's always bothered. Let it go. Okay, that's just what we call it, KMT theory. There's going to be things called ideal gases and things that are called real gases. An ideal gas is pretend. They don't exist. It's hypothetical. We say if everything was exactly perfect, what would happen? It allows our math to be much easier. If it's not an ideal gas, if you're going to try to make all the little corrections to, how things behave, your algebra equation gets really, really complicated. It's doable. In college, you do the correction values, but we're not going to worry about that at high school. We're going to pretend that everything is ideal. One thing we sometimes might ask you is what conditions would allow a real gas to behave like it was ideal? So real gases can behave pretty good under certain circumstances, certain conditions. So we want to have a very high temperature so that they're going very, very fast. And we want a very low pressure so that they're very far apart, because we don't want the molecules interacting with each other. So it's best also if there's very low intermolecular forces, like things that are nonpolar, things that are small, right? They're going to behave more ideally. If the molecules start interacting with each other, things start getting off track, right? So we want them to go really fast, be very far apart, and basically ignore each other as best as possible. So there's kind of 5 assumptions of KMT theory. I've seen people break this into more pieces. I've seen people condense it into, fewer. I always go off of 5. I think 5 is the one that's easy to remember. I like how they're chunked. So the first one is that gases consist of large numbers of teeny tiny particles that are very far apart compared to their size. We want to say that most of the volume of a gas is empty space. The gas particles we pretend are so small that they don't have a volume. We know that's not real, right? Remember, these are for ideal gases. We're pretending here. I know that they have a real volume, but it's very, very small. So if it was a perfect world, they would be what we call point particles. They'd have no volume. And then one more thing to remember is that they're further apart compared to a liquid, compared to a solid. Collisions between gas particles and the container walls are what we call elastic. So when a particle hits a container, or when the particle hits another molecule, we're not going to lose any energy. In real life, like imagine you throw a ball against a wall and it bounces off and it keeps bouncing and it's bouncing all around off the floor. Eventually, it starts losing energy, transferring it to the surfaces it's hitting, transferring it to the air, and slowly but surely the ball would stop, right? But the gas particles don't behave that way in an ideal gas. So we say that when the 2 molecules hit, or when the molecule hits the container, they transfer their energy, but they don't lose it. There's no loss. They just hit it and move and they keep going, right? So that's something that's a little bit different than a real gas. Gas particles are in continuous, rapid, random motion. They therefore possess kinetic energy, which is energy of motion. They move in all sorts of random directions non-stop. Number 4, there's no forces of attraction between gas particles. You'll hear people often say they behave like billiard balls, which is like the game of pool, right? The hard spherical balls that don't have an attraction or a repulsion for each other. We know that in real life that molecules have intermolecular forces, right? There's attractive and repulsive forces, right? But, we're pretending that these gas particles don't interact with each other. The next part, oops, my animations are off, oh well, is that the temperature of the gas depends on the average kinetic energy. So you can see here, Ke, kinetic energy, is equal to 1/2 the mass times the velocity squared. So as your temperature goes up, your velocity goes up, therefore your kinetic energy goes up. So temperature is not a thing in and of itself. Temperature is a way that we measure how often the particles are hitting, how fast they're going, how much energy they have, right? So if those things go up, our kinetic energy goes up. Last slide, properties of gases. There's 5 properties. I kind of like thinking of KMT theory with 5, assumptions, and there's 5 properties of gases. It helps me remember it. Gases expand. They do not have definite shape. They do not have definite volume. They fill the container they're in. They're what we call fluid. There's no attractive forces between the particles. They just slide right past each other. They flow. They're low density, meaning they're very far apart, and there's not a lot of particles for each given volume. Because they're very far apart, they can be compressed. They have compressibility. So you can compress them, squish them closer together. Think of an oxygen tank. The last one is something called diffusion, meaning that the particles will mix together, right? If I have a container of really strong perfume in one corner of the room and I open the lid, eventually someone in the back corner of the room will be able to smell it because the particles will slowly mix. They're bouncing all over the place, right? And so they will slowly expand the container to fill the room. They slide past each other, right? And they're going to be able to fill in and they'll diffuse and mix with the other particles. Okay. All right, so that's a real quick overview of some of the key things that hopefully you remember that you learned in middle school. If any of those are confusing, come talk to me. I can give you examples. I can diagram things. We can work it out. Okay? All right, everybody. I hope that was helpful. Bye.